All right, now we're continuing with polar graphs. Sorry, the calculus part of polar area and arc length and all that. So we talked about in the last session how to find the area of one leaf of a polar curve. It can be that you're going to be needing to know, like we did with the area between two curves. You might have one curve and another curve, and you might say, well, what's the area between those two? And of course, we know that at that stage, we're going to have to know, well, what are the points of intersection? What is this A and what is this B value, so that I can set up my integral from A to B. Well, the same thing can happen with polar, so we need to know how to find points of intersection. Now, just like what we would do with this rectangular one is, if this were function f and this were function g, we would set them equal to each other and solve for x equals a and x equals b. So this would be sort of the thought process. Now, for polar, it's really the same thing. So if we were to ask, well, where does r equals 1 minus 2 cosine theta intersect r equals 1? Well, if we found those points of intersection in the rectangular world by setting them equal to each other, it seems logical that we would set these equal to each other in the polar world as well. So if we do that, we'll have the first r, 1 minus 2 cosine theta, set equal to the other r, which is 1, and solve for theta. So subtract 1 from both sides, divide both sides by -2, and then find the angles where that occurs. And of course, cosine of theta is equal to 0 at pi over 2 plus pi n. So, if we were to look at the graph of those two functions, polar graphs, we would discover that, let me set this up. Oops. Oh, wow. Well, that looks really awful. Let me try again. Okay, so here's my polar grid. And r equals 1 minus 2 cosine theta. I'll represent with a red graph. Let's see. And that would be a lemma with an inner loop. So let me get this set up. And go out here to 3. Like that. Okay. And then the graph of r equals 1 is a circle with r equal to 1, which is in green. Now, if we were to start listing a couple of values where this occurs, according to the algebraic approach that we just did, we would have theta equals pi over 2, and then 3 pi over 2. And that would probably be enough, because that finds, in this case, let me color code this, that pi over 2, cosine of pi over 2 is 0. 1 minus 0 is 1. So pi over 2, 1. That's this point of intersection right there. And then the other one, I'll color this color, is at 3 pi over 2. Cosine of 3 pi over 2 is 0. 1 minus 2 times 0 is 1. So at 3 pi over 2, we're right there, just that point right there. Now the question is, do you see any other points of intersection? Unfortunately, you do. And let me explain what's going on here. The difference between points of intersection and visible points of where the paths cross each other is this. Let's say you have two satellites. If they ever are actually at the same place at the same time and crash, they've become ineffective. So you might not want that to happen, to be at the same place at the same time. So in other words, what we're finding here, algebraically, are the places where they're going to crash when they're at the same place at the same time. In other words, they're at the same point given the same angle. Now, is it possible that the two satellites would actually have different paths and they would cross each other's path without ever actually hitting each other? Well, of course. And so if we look for where the trails cross each other, their paths cross each other, that's a whole nother thing other than setting them equal to each other, which means same place, same time. We're finding the ones that we see on the graph that were not found algebraically. That's where their paths cross, but they're not there at the same time. Let me show you what happened there to make this a little bit clearer. At theta equals 0, the red graph is 1 minus 2 cosine of 0 and cosine of 0 is 1. 1 minus 2 times 1 is negative 1. So when theta is 0, the point is with a negative r right there, where it's at the path where the paths cross, right there on the left side of the y-axis, where I just pointed the arrow. But at theta equals 0, for the other graph, r is positive 1. So at that same point in time, this is at that point. They're never there at the same time. So what you'll have to do is make sure that you distinguish between those, and you may have to actually graph to find where the paths cross each other. If you're looking algebraically for where they would be there at the same place for the same angle, which is what we generally would want for our problems, then just solve an equation where you set the r's equal to each other, as we just did. All right. So if you go to the next page, it talks a little bit about finding points of intersection of two polar graphs being like where you're going to collide two satellites. And so you can read that page and see. It's kind of what I was talking about earlier. So let's go to example 2. Find the area of the region common to the two regions bounded by the curves r equals, oh, I'm still in green. I guess that's okay. Negative 6 cosine theta and r equals 2 minus 2 cosine theta. All right, so let's set up a graph so that we can see what we're talking about here. And let me get some circles here for our polar grid. Let's see, how many will I need? 1, 2, 3, 4, 5, 6 of them. Yeah. That's 3, 4, 5, the bigger they get, the worse they become. They don't look very circular to me anymore, but hopefully you can indulge me on this. Not the best graphing polar and circles and stuff with my freehand going here. All right, so r equals -6 cosine theta. Let's graph that one first. R equals a cosine theta is a circle. One of the points on that will be at the pole, and the diameter, oh, I'm sorry, first the center is going to be on the x-axis because it's cosine, and cosine is related to x, and the diameter is 6. But this negative is actually going to make this an interesting variation of what we've already talked about. Think about if cosine of theta, or cosine of 0 is used. Angle 0, cosine of 0 is 1, -6 times 1 is -6. So this circle will have its center on the x-axis, but it's going to be on the left side. So if a is negative, for cosine it'll be left of the y-axis, and if it were doing r equals a sine theta where a is negative, instead of above the x-axis, that graph will be below. So just an interesting little thing. So at 2 pi over 3, cosine is 1/2, so that'll be -3. Did I say pi over? I forgot what angle I said. Let me back up. Pi over 3, cosine of pi over 3 is 1/2. So if we're at this angle and we get a -3 answer, -6 times 1/2 is -3, that's going to put a point right here. And if I go to -pi over 3, the cosine of -pi over 3 is 1/2. So I'll also get a -3 for that. Okay, so we get a circle that looks like this. All right, for the red graph, 2 minus 2 cosine theta is going to be a cardioid, and it's going to have major values at the pole. Pi over 2 is 2. Pi, let's see, cosine of pi is -1. 2 minus 2 times -1 is 4. So pi will be out at 4. 1, 2, 3, 4. 3 pi over 2 is 0. 2 minus 2 times 0 is 2. And it gets us back. So that cardioid looks like this. Not a good graph, not a well-drawn graph. I am so sorry. So what we're supposed to find is the area of the region that's common to those two regions. So it's where they overlap. So let me set up a different color here. And we're talking about all of this region where they overlap. Okay. So now it's going to take a pretty good picture of what's going on, better than I just drew, to really understand what's going on. So let me just kind of freeform draw this. See if we can make this make sense. Okay, so there's a place where they intersect right here. And there's another one, of course, but what we're going to use is symmetry, because if we do the area above the x-axis and double it, that'll give us the full area that's enclosed in common between them, or with them both considered. So until I get to that point where that occurs, the angle that creates that, let me do that in a different color so you can see it better. Try this color. Until I actually get to that point, I'm using the circle to get this part right here. Okay? And then after that, I'll be using the the cardioid as the boundary. So it's going to be inside of the circle until we get to the intersection point, and then inside the cardioid. So that's really an important point to make, is that the point of intersection there has to be found. So let's do that first by setting these equal to each other. 2 minus 2 cosine theta is equal to negative 6 cosine theta. So I'm going to add 6 cosine theta to both sides. And subtract 2 from both sides. Then divide both sides by 4. And the times when theta equals negative 1/2, the cosine of theta equals negative 1/2 is at 2 pi over 3 plus 2 pi n, or when theta equals 4 pi over 3 plus 2 pi n. All right. So if we look at our picture, since we're only using the top half, we only really need to use 2 pi over 3 for this. So the point of intersection that I'm interested in is this one, which is at 2 pi over 3. That's what theta is there. So to find this area then, we're going to find, let me change colors here. To find that area, we're going to find the area of half of it. So what we're going to do is we're going to double the following. Now, the first part that we're finding is that what I put here in kind of that purpley color, we're inside of the circle from the beginning of that, which happens to start, let's see, when are we at that place? It's pi over 2. There we go. Had to see it. Sorry. So we've got 1/2 of the integral from pi over 6. I'm sorry, pi over 2. Don't know where pi over 6 came from. To 2 pi over 3. Of r squared, and since we're within the circle at this point, the r that we're going to use is the negative 6 cosine theta squared d theta, plus, now to get the aqua region, we're going to do 1/2. We're going to pick that up, start what's within the cardioid curve, starts at 2 pi over 3, the part of the region we're looking at, and ends at pi. Because remember, we're doing half of it, so we're stopping at pi when we get to this spot right here. That's where we're stopping. Of r, which in this part, it's the cardioid, so that's 2 minus 2 cosine theta d theta. Okay. And then we could do all that integration and simplification, and we'll come up with 5 pi over 2. And if you need to ask me to see those steps, that's all basically prior material that we've talked about before. The 36 cosine squared theta, you'd pull out the 36 and replace cosine squared theta with 1 plus cosine of 2 theta over 2. It's that power reducing identity. Oh, and I forgot to square this over here. Glad I looked back. And here you'd have to square the binomial, getting 4 minus 8 cosine theta plus 4 cosine squared theta. The constant would be easy. The cosine theta would be easy. Cosine squared, you'd again have to use that power reducing formula. So again, if you need help with how to do that, I can address that during office hours, or during class, excuse me, during class. And I'll be happy to do so. But I'll leave that to you as something to practice on and see if you can get that 5 pi over 2 without a calculator and see how you do with that. All right. Oh, I'm sorry. You know what? That was before I multiplied by, I forgot to multiply by the 2. Let me go back. Oh my gosh. Okay. I might insert this. My bad. I got to multiply. I was doing the integral part. And, sorry. And so after we multiply by that 2, we do get 5 pi. I could lie to you and say that I did that on purpose, but that's actually a pretty common occurrence. And you see I did it too, is you could do all that work in that initial 2 that you multiply by, you could accidentally drop it and not use it. So please make sure that you don't forget that constant of 2. In fact, I would probably distribute it at the outset if I were going to show you all this work, and I wouldn't forget it that way. But I did forget it that time, so I do apologize. All right. Now, one of the things I might ask you to do is not to actually find the answer, but just come up with an integral expression that would find the area between those two. And so I might do that, and that would be simply the first line, a equals 2 times the rest of that stuff. And I may not ask you to finish it. So do please pay attention to the directions. You see how much work you could cause yourself if you did more than just set it up. All right. So next topic is arc length in polar form. This is going to sound very familiar. It's going to be very familiar to what you've already seen. So that the arc length formula, I'm not going to develop the whole thing with you. I'm just going to tell you what it is if you want to find the arc length, you're going to go from alpha to beta, and you'll take the square root of the function of theta, or r, I'm going to call it r because I think that's simpler, squared, plus the derivative of r, dr d theta, squared d theta. So it is necessary that you have a continuous function, and its derivative has to be continuous. Then this will be your arc length formula. So let's do our first example with that. Example 3. From theta equals 0 to theta equals 2 pi for the cardioid r equals 2 minus 2 cosine of theta. All right. So the first thing I would do is, after I've made note of the fact that r is 2 minus 2 cosine theta, so I would go ahead immediately and find dr d theta, because it's part of the formula that we're going to have to use. The derivative of 2 is 0. The derivative of negative 2 times cosine theta is negative 2 times negative sine of theta, so that ends up being 2 sine of theta. All right. And so we set up the integral for this. They told us to go from 0 to 2 pi, so we're going to do exactly what they said. Follow the directions. And so our integrand will be the square root of r, which is 2 minus 2 cosine theta, quantity squared, plus dr d theta, 2 sine theta quantity squared d theta. All right. So let's simplify this one, go through the algebra of it, because this one's kind of interesting, I think. So doing the squaring, we should get 4 minus 8 cosine theta plus 4 cosine squared theta plus 4 sine squared theta This may seem like, oh my gosh, what a complicated thing. Well, the good news is they gave us something in here that's really going to help us a lot. The 4 cosine squared theta plus 4 sine squared theta. If you factor out the 4, it'll be 4 times cosine squared theta plus sine squared theta. And the trig identity, the Pythagorean identity for cosine squared theta plus sine squared theta is 1. And so that underlined thing will be 4. And then we'll add it to the other constant 4 that's already there. And we'll have the square root of 8 minus 8 cosine theta d theta. Okay. So if we factor out the 8 and then split that into 2 radicals where it's square root of 8 times the square root of 1 minus cosine theta, that square root of 8 part can come out in front. Simplifying, that becomes 2 square roots of 2 times the integral from 0 to 2 pi of the square root of 1 minus cosine theta d theta. All right, so I'm going to go off to the side for a second and do a little lemma, a necessary piece of work to allow us to keep going is called a lemma. I've seen 1 minus cosine theta in an identity before, and this is where your knowledge of identities is really crucial. I know that if I divided it by 2, that's going to be sine squared of half of that angle that's given. Remember, when we're doing power reducing, we double the angle, so if we're going backwards, we have to take half of the angle. So what I could do with this identity is multiply both sides by 2. To get a replacement for 1 minus cosine theta. And that's a really good thing. Oops, it's too high. It's a good thing because that perfect square under the radical makes me happy. Okay, so if I take the square root of that product 2 and sine squared of theta over 2 and split that into radicals, that constant will be square root of 2. And if I take it out in front, 2 times square root of 2 times square root of 2 is 2 times 2, which is going to become 4. And we'll have left the square root of sine squared of theta over 2, which is going to simplify to be sine of theta over 2 d theta. So we finally came down to something that's actually pretty easy. So the antiderivative of sine of kx, or here k would be 1/2, is 1 over k, so 1 over 1/2 times negative cosine of kx, so to speak. Okay? And that'll be evaluated from 0 to 2 pi. So 4 divided by 1/2 is 8, times -1 is -8 cosine of theta over 2. So starting to do the substitution, put in 2 pi first, minus -8 cosine of 0 over 2. And that simplifies to be 16. I'll double check that. Cosine of pi is -1. -8 times -1 is 8. Minus -8, so that's plus 8 times cosine of 0. Cosine of 0 is 1. So plus 8 times 1. 8 plus 8 times 1 is 16. Yep, that's right. Very good. So let's stop here and continue the rest of the notes in another portion.